Welcome everybody. Super excited to have you. We have a really fun guest today. We've kind of swung the pendulum back from, bioscience AI last week to, now we're going to do atomistic simulation this week. And so Eli is joining us. Eli is one of the co-founders of Rowan Scientific. Did his undergrad in computer science, and then went to a prestigious program at Northeastern for graduate school. Before shortly realizing that there were many more interesting things to do at Rowan and dropped out to build this company. And so I've been an admirer of Rowan for quite a while because they do wonderful open science for the community. Very, very nice blog posts, and they build these beautiful tools for reproducible and fast simulation in science. So ticks all the boxes. I'm really excited to have Eli here today, and feel free to take it away.
Cool. Yeah, thanks so much for having me, guys. I'm excited as well. Cool. I'll start by just sharing my screen here. And all right, oops.
And I'll briefly mention while we're getting started, we have an additional panelist today, Christoph, who runs our structure teams at GenBio. And so we're trying to get a little bit closer to the domain that Eli works in and that GenBio works in and try and bridge the gap here. So welcome, Christoph. Thanks for being here.
Yeah, thanks for having invited me.
Cool. Okay, yeah, can you guys see my slides?
Yes.
Awesome. All right, cool. I'll get started. So yeah, I'll be talking about our most recent paper, Egret-1. It's sort of some foundation models for bioorganic simulation on the molecular level, and then briefly I'll say a few things about Rowan, and then we'll open it up for questions. So we'll start with okay, yeah, like why do we care about simulating atoms at all? Why is this sort of a thing important? And in short, it just makes it so you can make better use of time in the lab. So, if you're able to run lots of experiments in simulation before you even get to the lab, you can, instead of wasting a bunch of time doing experiments that lead nowhere, you can screen a lot of things out in silico and then focus on what matters with your time there. So, this leads to, more successful experiments and then, just more drugs being designed. Another thing that it allows you to do is just like observe things that are hard to observe in a lab. So an example would be like a reaction pathway is like hard to experimentally observe, but you can model and observe this sort of a thing in simulation. Like more broadly, simulation just like allows for uh, it's a thing that just like sort of accelerates field. So just for example, like if we look at semiconductors, for example, you're designing and you're doing a lot of simulation, in SolidWorks or whatever it may be before actually fabricating any chips. And then once those are fabricated, if you've done a lot of things in your simulation, then you have a higher likelihood of, after going through that expensive process, getting something that works. So in our example, the expensive process is doing something in a lab. So yeah, this is just why we care about this thing. Having good simulation tools makes a field just like sort of explode. It has the potential to do that, and just have it yield a lot more useful things. In this case, drugs. Okay, so how do we model molecules? All of like the physical laws necessary that sort of model what's going on at this level are known within the Schrodinger equation. However, this is intractable. It's just too big to actually simulate. So we need to do approximations. I'm going to keep it like sort of at a high level for these approximations because it's not necessarily my expertise, but for like our high level of theory approximation, we'll consider density functional theory. So you guys can see my mouse, right?
Yes.
Yes.
Okay, yeah. So they sort of fall. This is a graph of conformer ranking. So you want low error and you want it to be fast. So conformer ranking versus time. So you have your like DFT approximations. They take a long time, but they're highly accurate. And then you have your semi-empirical approximations, which is like we'll model some parts of the Schrodinger equation, but for the hard parts, we'll fit some empirical parameters. This sort of uh, you'll have bigger errors, but you can do things a lot more quickly. And then you have your molecular mechanics, your force field. Sage is an example of one of those, where you ignore all quantum effects and you're pretty much just pretending a molecule is just balls and springs with like this sort of momentum, and you're using just like mechanics to model these things. So you get a lot higher error, but that you can do this super fast. So this is like um, this allows you to do things like molecular dynamics on super large systems like proteins, but they're not uh, as accurate as your other methods. So what can like neural networks do here is like this is just an example in green here of some recent neural networks and where they kind of break the trend on this Pareto frontier where look, your models like AIMNet, for example, you can train highly expressive like neural networks on data generated from DFT results. And if you can approximate those really well, given, you can verify that they generalize, you can have really accurate simulation at a fraction of the cost. So like you're getting like DFT accuracy orders of magnitude faster, and hopefully one day it's just as quick as force fields. The idea here is you're just you're fitting a highly expressive function on known labeled data about molecular simulation, hoping that it learns some shortcuts to the Schrodinger equation and takes into account those quantum effects. So neural networks now can be used as like really optimal tools to do things that we've never been able to do before in molecular simulation. So what is a neural network potential? Like essentially it's just a regression model. The input is a set of atoms in 3D space. And the output is just the energy across that entire system, and then the forces that are acting on each individual atom in that system. So um, a very common way to represent these is as a graph. So oftentimes we use graph neural networks here. Right here, I have an example of ibuprofen. This is just kind of like 3D representation with covalent bonds. It's like very natural to represent a molecule as so like the atoms in a molecule as nodes on a graph, and then like their bonds as edges in that graph. So if we kind of imagine like this is our a graph, a node on the graph can be defined as, if this is node I, it's the atomic position, the position of the atom, the atomic number. So like what atom is this? And then the hidden state, which is like how are we representing this in, however many dimensions we choose. Um, Usually in these neural networks, we're not actually just doing a covalent bond graph, but we have some sort of cutoff distance. So for like a neighbor for an atom I, um, if something falls within some cutoff radius, then it will be considered a neighbor, and we'll add that connection in like our graph representation of the molecule. Um, So like what makes these things like expressive? What makes them why recently are we seeing these becoming super useful and like accurate tools in this space? There's a lot of reasons, but a few of the main ones I'll mention here is like the message passing neural network architecture, equivariance, and high body order. So these are things that allow for high expressivity and pretty accurate approximations. So if you remember that our node state can be represented by like this sigma, and it's our position, our atomic number, and our hidden state. The most basic like formulation of a graph neural network is just a graph convolutional network. So the way you update your hidden state is you iterate over all of the neighbors. So this is your hidden state for a specific atom or node in the graph. Um, you take all the neighbors of that atom, you multiply it by a weight matrix for that passing step. You which is here. You have your and the step is defined by t. So like one iteration is like t. So you have a different weight matrix for every time that you're like sort of doing this operation. You're multiplying by some regularization term, and you're taking the sum. So it's pretty simple. It's a weighted sum across the neighbors of the graph. And then if you're going to predict something like energy, you have like some sort of MLP. Oh, and then obviously, you have your nonlinearity between your graph convolutional layers. But yeah, you predict an energy. You'll take your scalar from like this hidden state vector for all of your nodes at your last step, so your last like layer in your network, and just regress on some scalar. So a message passing neural network extends this. It's similar. It's just you know it you have more parameters, you have a little bit more expressivity here. So before you know how you update your hidden state, you need to compute a message. So the flow of information, like the interactions between two nodes on a graph, are modeled by some learnable message function. So this is where a lot of your learnable parameters are going to be. And you update, and your message is defined by the sum of this message function across all of like the neighbor pairs in your graph neural network. And then you update your hidden state. Oops, sorry. You update your hidden state by some other learnable function that you take your message that you've aggregated across all of the neighbors, and then you combine it in some way with your current state of your current node, and then you update your hidden layer. And then on the output, each individual node has some other readout function. So like your state of your node at the final message passing step, you have some readout function that will be another, a learned classic ML style. It's a learned function. And then you take the sum across all of these if you want to get your total energy. So yeah, this is just like a more expressive way to it allows more degrees of freedom than like a graph convolutional network. And I'll use this message creation step as a way to explain these other two. So um, to explain like just like equivariance, let's just say that we have G of T, which is just some set of nodes. So some set of atoms and their states. So it's just like their positions, their atomic numbers, their hidden states. And this is like what you pass into your message function. So a message function is said to be invariant to a given transformation if when you apply this transformation to your input of that function. So if you apply a transformation to this set of atoms, then you're going to get the same output of your message function as if you never applied that transformation to begin with. So just an example of invariance here is like one of the reasons we use graph neural networks. Not only is it like a natural way to represent a molecule, but they are permutation invariant, meaning like it doesn't like the order in which you feed there's no order in which you feed the network your atoms, for example. Like all it cares about are what are the nodes, so the atoms, and then what are their neighbors, what are they connected to. Um, and so yeah, and then equivariance is similar. Invariance is a form of equivariance, but this pretty much just means that a message function is said to be equivariant if when you apply a transformation to the input of the function, the output of the function is predictably transformed. So if you do some transformation t to the input g of t, then the output of your function should be uh, predictably transformed by t prime of your message function on g of t. So one important indication here is you should be able to easily like get t prime from t. So like it should be some function of t prime that's structured in some way. So that's a very abstract way to ground it in something that we use a lot for here for that you see a lot for neural network potentials is SO3 equivariance. So this is like a type of spatial rotational equivariance. This means that if you rotate the input, so if you rotate, the R positions of your nodes that are being input to your message function in some way, then the output of that message function will be rotated in the same way. So in this case, the T prime equals T. It's the same. Uh, it's the same transformation. And we do this just to like we're adding some inductive bias to the models. So it's like molecular data is like it's expensive, it's hard to come by, and the space that you're sampling from is so huge, it's really hard to like truly model a distribution. So by adding these things that we know are true about the space is like SO3 equivariance. We're adding this inductive bias and decreasing like the size of the parameter space that the function needs to optimize over. So you're just trying to making it easier for the model. And this allows for better sample efficiency and things like that. Another thing is high body order message construction. So on this example on the left, we have like a two body message, meaning like the message captures like the signal or the interactions between all pairs of nodes that include your current node. So the message for a given node is like the sum of the message function across all pairs that of connected neighbors in the graph that include that node. Um, but you can extend this to a greater number. So if you have like a body order of 3, it will be all triplets that include that node. So one message is being like, okay, like what are the forces or what are the interactions going on between these three? So if you have a high body order, you're usually including the lower body orders as well. So it's like if you have a body order of 3, you also include the body order of 2. And the one body order, which is just like how does it interact with itself, that's kind of like subsumed into your update function here, at least in this sort of like nomenclature. But yeah, this is important for things like, dihedral angles, for example, um, are something that you wouldn't really be able to capture with just like pairs. You would need triplets, or yeah, or even higher body orders can just like allow for more expressivity. Um, so, modern architectures, all this to say, modern neural network architectures, because of these things, like are super highly expressive. Um, the only problem is, part of why we did this work is a lot of the open NNP work was for materials. So we see like OMAT 25, it's a huge work by Fairchem to make NNPs that can predict materials, crystal structures well. Orb V3 is another example. The first MACE MP0 model that's open sourced. GemNet, Open Catalyst, and this was mostly driven by efforts be like the Open Catalyst project. It's like a public benchmark saying like, okay, how well can you make an NNP on this Catalyst benchmark? So it's like it's a material. So people are putting a lot of time and energy into making these sorts of things. There are open source, or there are some, before we did this work, there are some molecular models that are just like designed for molecules in this space. AimNet2 is one, for example. We use it a lot in Rowan. We love that model. Another one is MACE 23. And if you've read the paper, our models are like almost clones. I know they're super similar to those models. The only problem is the MACE 23 models aren't fully open source, so they're academic licensed. So we wanted to make a model that was open source that we could use, and then other people in industry could use as well. Even just as like a side note, the MACE models, even like the ones that are used for organic materials, they're trained on organic molecular data sets, but they still like the architecture for um, is designed for materials, and you can see that in the fact that like there's no global charge input because that it's not really relevant for a material, or like multiplicity, for example. Um, so yeah, the most of the neural networks, the technology is there. Most of the open source work is for materials, and the available data sets for uh, organic molecules were not great. So like they're small, low diversity, or low level of theory. There's just an example of some of the main ones that existed when we did this project. So we have Spice, which we actually include this in the data sets that we train on. But it's 2 million structures over 17 elements at a high level of theory, Annie 2x, 6 point or 9.6 million structures. It's at a mixed level of theory, so some high level, some sort of medium, low level. And then QM9 is a pretty famous one, only 5 elements, low level of theory. Um, one caveat here is now there's actually like, pretty shortly after releasing this paper, there are some pretty awesome data sets for this, for organic molecules and things. Um, AimNet2, they released their data set, they open sourced it. It's 20 million structures. It's a mixed level of theory, but the AimNet model performs really well. I think this is probably going to be a really good data set, especially if you like take charge into account and have some way to do that like AIMNet does. It's across 14 elements. And then, OMAL 25, it's like, this is huge. It's 100 million structures across the full periodic table, high level of theory, and it's super diverse. I mean, this is a bio seminar series. It contains proteins, it contains all kinds of things. Facebook really did like awesome work. The guys at Fairchem did awesome work in releasing this data set. So now there are some pretty nice open source data sets. I'm excited to see what people do with it. But part of the problem that we were trying to address here was, we have our neural network potential. The technology is good. People aren't really training them for organic materials, and there aren't great, organic molecules, and there aren't great available data sets at the time. Another thing is that existing neural networks at the time, even today, like they're just like not very well benchmarked. Like they're benchmarked well.
Sorry, like very good question. What do these data sets typically contain? Like what kind of information? Is it structures and energies or also other things or?
Yeah, that's a really good question. So it's they contain DFT. So oftentimes it's just like uh, it will be data based on like structures that were computed at different levels of theory. Oftentimes it will be like DFT. There's some big data sets of like semi-empirical calculations, but what it is yeah, it's energies, it's forces. Some of them have dipole and quadrupole moments. Um, most of them don't have like your full orbitals, but I don't know why you wouldn't necessarily need those things. But yeah, it's large data sets and it's energy and force labels that you would train on. Yeah, does that
Okay,
answer your
thanks.
question?
Yes, it does.
Okay, cool.
And so is this energy labels atom wise or overall?
No, that's a good question. So yeah, the usually when we're looking at a molecule, we are predicting like a single scalar of potential energy across the entire molecule, and then for each individual atom within the molecule, you're predicting the force that is being, the force magnitude and direction that's being acted on that atom in the molecule at a given time. Um, but yeah, a lot of um, neural network potentials will like predict individual atom contributions to the energy, which aren't like actually physical. Like they're useful for when you're just predicting things like, okay, what's the contribution of each individual atom, which doesn't correspond to anything like real. And then you sum those and then you get your actual energy. So like in model design, we look at like atom contribution to energies, but usually, and then especially in like modeling, what people care about is like the potential energy across the entire molecule.
Okay, super cool. Yeah, I was wondering because I took a look at the very, very nice introduction to NNPs blog post before this, and one of the things that was mentioned is yeah, the overall energy is a sum of the contributions of the atom energies, but also this force constraint is really important, and you can get that from the atom-wise potentials, right?
Yes.
With respect to the derivative of that with respect to the input coordinates, but there's no actual constraint other than there's no energy constraint or readout label for the atoms. It's just the force.
Yeah,
Is that
yeah,
right?
yeah.
Okay.
I'll touch on that briefly later, but yeah, when we have like individual atom contributions to the total potential energy, that's just like a way that we those are like artificial things we create because it's a useful way to create our model, but it doesn't correspond to anything actually physical. One thing that you mentioned was when you're getting the forces, one way to do so is like the conservative way to do forces is you take the gradient of the potential energy of the entire molecule with respect to the position of a given atom, and then you add a minus sign, and then that's the force of your that's the force on a given atom. So it's not necessarily the gradient of like the atom centered energy, but it's the gradient of the entire energy with respect to the position of that atom.
Oh, okay. I see. Okay. So the actual atom energies have it's just a useful sort of machine learning trick.
Yeah, yeah, yeah. There's not like no one's gonna. Yeah, yeah, yeah. Like no one's gonna want like a model that's like, oh, like how can I get the individual atom energy like of your molecules? Like no, like all right, throw it out the window. Yeah, it's like not it's not a thing that when people are doing molecular modeling, people actually look
Okay.
at.
Gotcha. Thanks.
Um, Okay, but yeah, existing NNPs are poorly benchmarked. So that's another um, thing that we're kind of trying to address here is they're poorly benchmarked if you want to use them as tools and you are like a chemist who wants to be like, okay, can I trust this as like a DFT replacement or not? They're super useful if you like are trying to publish your paper in like iClear or NeurIPS or something. When you have a nice like loss go down graph with bolded things. Like it's like, okay, yeah, this model, this architecture is great. It's making the loss go down. Um, but we find that like when we're actually, using these tools, or we're using these models as like tools in real workflows, the energies that have like, or the models that have like really low losses on the energies and the forces don't necessarily like perform super well on like things that we actually care about. So, uh, and this is how like pe people in general just like show performance of their models. It's just like in a very like ML coded way. It's like, we're doing ML for chemistry, ML people moving over to the chemistry side. This is how like in the ML space, like we know how to be like, okay, these are benchmarks, these are our results. This is how we show that we've done well. In a paper called Forces is Not Enough, there's like an example here of um, it kind of just shows that like a low error on force predictions doesn't necessarily correlate with good experimental or sorry like things that we actually care about predicting. So for example, like or care about using these for. So for example, on the left here we have like uh, MD stability. So we want this number to be higher. And then, force energy, force error. So this is obviously this number is lower. We don't really see a big correlation between, does this do stable MD and is the error on the forces low? For RDF, and this is on water molecules, by the way. The RDF and diffusivity, they do show a bit more of a correlation. But this is just sort of an example of like, just because you regress well on your energies and your forces doesn't necessarily mean that like it's hard to be like, okay, it does well for that. Like, can I do a torsional scan on this and trust it? Or like, can I do MD on this and trust it? Can I do, a conformer search using this as a backbone um, for optimizations? I don't know, I guess. So yeah, so what are we doing here? We're trying to address these holes. So what do we do? We generate a large and diverse data set at a high level of theory. We're training state-of-the-art NNP architecture on this data set, extensively benchmark it so people can look at this and be like, okay, like we we can trust to use this as an actual tool or not. If it does on the benchmarks, it doesn't do well on, maybe I wouldn't trust it for this. What we really care about here is chemists who are doing experiments. How can I look at this model and choose when I should use this and when not to use this. And then even for us at Rowan, like how can we inform which one what we recommend for which workflows and why. And then finally, we want to open source it under a permissive license. So MIT license models. Um, so we start by generating diverse data at a high level of theory, and we combine that with existing data. So the baseline data set was the data set from MACE 23 paper. So it's their MACE 23 data set. It includes most of the structures from Spice 1. It was one of the earlier versions of Spice. One of the most recent versions of Spice has a lot more things, but this one is an early version of the SPICE data set, and you've added larger molecules and then added some water clusters as well. So these are conformer ensembles, and this is like the baseline. This is kind of like the meat of the data set. We took a subset of OrbNet Denali. We're calling this Denali just D here, and this is just like weird stuff. We just try to take the weird stuff from Denali. This was trying to um, see like okay like we want to give like high fidelity data of weird things, so like hopefully this will help our model like generalize to be able to do weird things. So protomers, tautomers, salt complexes, and then like exotic materials just means their behavior is uncommon. Transition 1x, we took a 100,000 structure subset of transition 1x. It's transition states, and they're all neutral. Colli 3 plus 2, their reaction pathways on 3 plus 2 dipolar cycloaddition. So this is just more reaction stuff. Splinter, these are small molecule interactions. They're dimeric interactions, so not necessarily the interactions that aren't necessarily due to covalent bonding. So this can kind of like mimic protein ligand interactions. Vector QM, this is just like a really big set of a ton of different like organic and inorganic small molecules, and these are all ground state. So they've all been optimized. They're like ground state structures. And then Finch, this was actually a data set that we made in-house. I guess one clarifying thing is these are all subsets or examples of like public data sets that we took the structures and then we recomputed them at a high level of theory. We recomputed them to be the same level of theory as MESOF, our MESOF baseline. Finch was one Corin actually made using sort of like a metadynamic sampling. This is just like high energy conformers, so really strained structures, and then some solvated conformers as well. Yeah, so we trained a bunch of, we trained hundreds of different models or hundreds of models across a few different architectures on a bunch of different permutations of these data sets. And I know and this is like a kind of a dense table in a slideshow, so I'll just like, you can look at this if you want, but I'll also just like say what are kind of like the main takeaways here. One thing that we found was so yeah, when we tried with like many different architectures. First, we spent a lot of time on one of like the top architectures that is like really low error in energy and force predictions. And we found that we could get super precise on like this GMTK N55, which is pretty much, this is a measure of how well are you doing on your energy prediction. You want this number to be smaller. So yeah, how well are you doing on that prediction? And it had really great scores there and low force errors as well. But whenever we try to do like, we try to get some like gradients, so which is like a higher order, it's higher order value, like based on the energy, or then your Hessian, your frequency, even higher order. We observed like really poor behavior. So one thing that was important was like, okay, just because a model is really accurate, has really low error on your energy, it doesn't mean that it behaves well for your gradient. So it needs to be behaving like a smooth way. And then another thing too is a lot of models, what they would do is, or a lot of models currently what they do is they directly predict forces. So one of the outputs of your model is your potential energy of the whole surface. And then you have more outputs, which is like the force acting on every energy. So like in one inference step, you're getting the forces and the energies all together. And this is like pretty fast, but we found that this like ends up giving us forces that are not super smooth and not super well behaved, despite strictly enforcing SE3 equivariance, which is just rotational and translational equivariance. So one thing that we found was important was models that use a conservative prediction of forces yields a much more stable model. So rather than having a direct output of all of these things, what you're doing is you're predicting your energy, and then you're taking, like I mentioned before, taking the gradient of the energy with respect to the position of a given atom to get the gradient of that atom, and then add a minus sign, and now you have the force of that atom. Gradients are really easy to predict with neural networks, but this is obviously slower than predicting just directly. But we found this was super important to have good stability. Another thing too we found here is like more data does not necessarily mean better performance. Like just because all of our structures were at a high level of theory, we found that just like increasing the size of our data set didn't actually yield better results. We actually generated way more data than just these sets and what I show here. We don't have this in the paper, but we started with like 2 million structures from SPICE, and then we recomputed like 2 million more structures across like these data sets and many others. And we started by training our models just on those. And once we quickly realized that like more data does not necessarily mean better, we didn't include those in any of our experiments or in the paper because, the other subsets were even more sort of like diverse or weird, we figured if we can't extrapolate, if we can't pre-train on these sets, then we've got no chance and have good results, then we won't have good results by pre-training on those other sets as well. So these numbers here, just kind of these letters here correspond with the data sets I previously mentioned. T is transition 1x, C is Coley 3 plus 2, V is vector QM, F is Finch, D is Denali, and S is Splinter. So yeah, some of the main takeaways here. Yeah, so our biggest uh, pre-trained data sets don't necessarily yield the best results. We are okay. I mean, we're pretty good here on our energy predictions. We don't perform very well on the Baker gradients. We're fine, but much worse than just like our baseline set here. And then once you try to compute the Hessian, which is the frequency, which is the second derivative with respect to the position of your energy, you end up getting pretty large errors here. Um, so
Sorry,
another,
one very quick question. When you add these data sets, do you completely retrain the model or are you fine-tuning in some way?
this is completely retraining the model. And I guess one good clarification here is these are smaller versions of the model. So it's like uh, we in our paper we define like, okay, this is like small, medium, large, and which parameters, like which hyperparameters are associated with those. So like these are smaller models, but yeah, these are fully training smaller models across all of these sets.
Okay. And another question, I mean, probably the distribution of forces and everything is quite different in these data sets, no? Because some
Definitely.
of them are at equilibrium, some of them are not. So did you try to address this in some way? Because maybe like you just need different scales for the forces, for example, in different data sets or something like this.
Yeah, no, that's a great point. So one thing here is vector QM, for example. So this row here represents our baseline set plus vector QM, which was a really large set. So it makes our total data size a lot bigger, but all of the vector QM are ground state. So yeah, these are fully relaxed, whereas like our baseline are near equilibrium. So they're not fully relaxed structures. And one thing that we found was even though you get like this increase in data set size can like make your energy predictions lower, it actually sort of like softens your gradient, your force predictions. So your force predictions do take a hit, and then your higher order stuff takes a hit as well. And then we actually looked in and examined what were some of these force predictions, and we were almost always under predicting the forces because the forces are so small on the vector QM set, it biases the model to just the force predictions will all be biased towards zero. So yeah, that's a really good point. There's some papers, I'm forgetting the name of the paper now, but they show that like you can correct this by doing some like minor fine tuning. We tried this, it didn't work. I tried a lot of different fine tuning neural network potentials. It turns out to be really hard. Tried fine tuning this, being like, okay, you have your model that has a softened potential energy surface because your forces are too small because your data was too close to equilibrium. Take some strain structures and fine tune on that, and then you can kind of correct these things. We even tried this with like pre-training. So F represents a data set of really strained structures, and then V is our data set of ground state structures. Um, it didn't make the gradients better, and we also like had worse frequencies. But yeah, that's a really good question. And yeah, that totally that sort of distribution definitely makes a difference.
Yeah, did you consider something like data set conditioning? So you tell the system as an input that this is for in equilibrium, for example, or outside or something like this?
We haven't done that, no, but that's I think that's a really interesting approach. I mean, I've seen people do that for data multi-fidelity training. So they'll train on like some DFT methods and then some like semi-empirical methods, and they'll just have like, hey, this is semi-empirical, this is DFT, and then like have a higher weight for the DFT stuff. So
Yeah.
I think that's like definitely a viable option, but we didn't study that in these experiments.
Okay.
Um, so let's see here. Uh, okay, yeah. We also did like another thing that's not in the paper, but it's if you come to the talk or watch the talk, you get extra information. This was like our dynamic interaction subset. We train many models by changing the cutoff radius. So in all of our models, the cutoff radius is about 6, But since these are specifically with a data set of longer range interactions, we tried like, okay, what if it's 4? What if it's 6? What if it's 8? And we're trying to see like, oh, if you make your cutoff radius bigger, can you get these interactions better? The answer was no. And also the results were kind of, it was hard to draw a conclusion from that data because 4 was fine, 6 was better, 8 was like weird. It just there wasn't a lot of signal in that data, but it did tell us that, just having a bigger cutoff radius doesn't necessarily mean you can do um, these long range forces better. Um, so yeah, our final models we ended up with. So we took our subset configurations and we trained larger models on them. So one was the baseline model just on the MACE-off 23 set. This is sort of our general purpose model, generally more well behaved. Egret-1E, this one contains vector QM and the baseline. So this is like highly precise for energy predictions, but more unruly, higher order behavior. And then Egret-1T, this one was both reaction subsets added to our baseline um, to try to just get better results for reactions or transition states. So they're all based on the MACE architecture. They're almost all similar. They're almost exactly the same as the MACE-off 23 models. Same architecture, same data set, except we did expand. We trained them for a different amount of time. I think we had, some different training length parameters there. And then we had our cutoff radius was larger. But yeah, these models are MRT licensed. Um, I'll try to move more quickly now. I realize that I'm running low on time. Okay, so now benchmarks. How, you know, how do these models do on real tasks? How can we evaluate whether or not they're trustworthy tools? So we'll start with GMTK N55. This one is like a bit of a grain of salt. This is like a good way to show the energies are predicted. But as you saw in our previous examples, when we were designing these experiments, seeing which data to include, we were like sort of validating by looking at GMTK results. So like this is kind of like using a benchmark as a target. We didn't train on any of this data, but we did look at it when we were doing experimental design. So I will just say take this with a grain of salt. But one thing that this does show is we do have similar. I guess I'll have a lot of charts that look like this in this presentation. The green ones are our models. The white bars are other neural network potentials. The gray is a semi-empirical method, and then the blue ones are DFT methods. So we have comparable performance. Egret-1E is our best performing model for just um, energies, and we have comparable performance to other neural network potentials, but not as good as AIMNet. And this overall score is kind of like a weighted sum of energy predictions across a bunch of different subsets. So they have a ton of subsets that show just like different types of molecular interactions. And one thing that we're zooming in on here is just the barrier heights. Like barrier heights have to do with transition states and reactions. Like, does Egret-1T actually do better on these? And the answer is yes. So just by including that reaction data in pre-training, we can get better energies there. Can Egret accurately optimize geometries? So ROT32 or ROT34 is a geometry optimization benchmark. We actually do really well on these. We do better than even the DFT methods here, which is pretty cool to see. Can we differentiate between conformers? So Wiggle 150 was sort of that like Pareto graph, that speed accuracy trade-off graph that I showed you earlier. This is the same subset of things here. Solve NP conf is just another way. It's another conformer comparison benchmark. So it's like, can you differentiate between different conformers or shapes of the same molecule? We can pretty well. It seems like Egret-1, our general purpose model, does a lot better than the other two configurations on this set, whereas they're pretty even here. But as you can see, they're pretty on par with these DFT methods.
And so
Um,
identifying differences in conformers is going to be looking at like ranking, like looking for differences in overall energy.
yeah.
Okay.
Uh, yeah. So yeah, you have two different conformers of the same molecule. Yeah, what are the energy differences exactly?
And it's
Um,
looking like is the difference in energy like the correct direction, the proper magnitude according to like the I guess the ground truth here. Um, I guess how granular is that success metric? We have RMSD, so
Yeah, I'm not 100% sure about
okay.
this. But yeah, you can look at the both of these like benchmarks. There we have like links to those papers in our paper. You can kind of take a look at those. But yeah, I'm not 100% sure about that.
Okay, no problem. Thanks.
Um, so yeah, can we accurately predict the energies of torsional profiles? So let's say you take a molecule and then you rotate it around a specific bond. Um, in that sort of rotation, there should be like some sort of barriers, like energy barriers, where it's like, okay, it's not going to go, high energy torsions and then low energy torsions. And that's kind of like what makes this sort of useful here. So how accurately can it predict the energy across different torsional angles? Egret does on par with these DFT results, which is pretty cool. It yields stable molecular dynamics, and okay, this is not meant to be like dunking on Orb V3. Here, Orb V3 is trained on materials. This is on citalopram. It's like an organic drug. Like it's just not in distribution for that model. But it was really just to show like we can have stable MD over a longer period of time here. With these models. Uh, we can extrapolate to periodic systems, so we're not training on materials or periodic systems. We see that Egret-1 can extrapolate pretty well, better than these other NNPs and the semi-empirical methods. The Egret-1E and Egret-1T just they cannot. And then the Schrodinger crystal structure prediction benchmark, Egret-1, also does pretty well on these. So AIMNet isn't trained AIMNet and Egret aren't trained on these sorts of structures. Egret-1, it extrapolates pretty well. MACE and Orb are trained on these sorts of structures. So it's pretty cool that we can extrapolate in that way. Um,
The process of adapting something that was trained on these molecular structures to periodic systems, because it seems like you'd either have to have a whole different input or you'd have to be quite clever.
yeah, well, one cool thing about like neural networks for doing periodic systems is like it's not as complicated as if you're trying to do like DFT for this sort of a thing because since we're doing a graph neural network, the way that we have like our periodic boundary condition is we just construct the graph in a different way. So like if you have some sort of box around your molecule and then you have like one molecule on like an edge near the edge of a box and then sorry, an atom near the edge of a box and then an atom near the opposite edge of the box. You just construct your graph and you call those things connected. So it really just changes the way that you construct your graph, which is not even part of the model. You construct your graph, then you put the input. So it's actually like a pretty elegant like extrapolation to do a model on periodic systems and molecular systems for NNPs.
Okay, beautiful. Thanks.
So where does it fall in this Pareto frontier? Um, it falls around here. So with this work, what we were trying to do is like how useful or how well can we make a neural network potential perform? So it's not as fast as AIMNet, not nearly as fast as your force fields, but the accuracy is pretty much on par with a lot of DFT methods, and it's orders of magnitude faster. One thing we were even able to do was in 140 seconds on an H100, we could optimize like this small protein, human insulin, and yeah, this is just overlaid optimized structures, not optimized structures. So, it's fast compared to DFT. So
Sorry,
basically,
one may I ask a very quick question on before that? Yeah, so is there any like line there which you would say that below that you become useful and above it's probably less useful, or I'm just wondering like what is the relevance of like smaller changes at the bottom there?
yeah, I mean, I think like uh, I wouldn't draw a line to say like useful or not useful. Like for example, like Sage, like molecular mechanics are really useful for specific things, right? Because they're just so fast, you can actually do MD on a protein. But like you're not gonna you're not gonna just trust it for single point energies. If you want really high accuracy, you can do them here. I guess the point of this graph is really just to show like without any of the green, you have kind of like a pretty like you can kind of see this Pareto frontier, and it's clear that these neural network potentials break that. I think like um, I think I don't know. It seems like anything in this quadrant is like good, right? Like if you can do uh like if you can get a model that's like more like here, then that's pretty awesome, right? Like you can get like much better than molecular mechanics and around the same speed. Or if you can get something that's around here that's also good, obviously like the best would be, here
Mm.
here in this graph. But I mean, I consider all these NNPs useful, and I think semi-empirical methods are also still useful. DFT is still useful. It just depends on what you use them for, and like moving to new areas of this graph like expands, being like, oh, now we can like use this in ways that we didn't think were possible. Yeah.
Okay, yeah.
So yeah, are they trustworthy tools? We think so, based on these benchmarks. Like, are they useful? Um, so yeah, what is this relevant? How's this relevant for you guys? How's this relevant for like larger systems? The audience of this sort of a talk. Um, so one thing is like, Moore's law indicates that atomistic models will be able to scale to larger systems. As we kind of mentioned earlier, just in our discussion before the talk was, as you get to larger systems, you have to just like coarse grain out some of the more fine information. The idea is like, you know, we think that we'll be able to do, you know, make protein models that are atomistic, as we make these models more scalable, and then compute and hardware get better as well. So this is just an example from an Allegro paper. Allegro is a type of NNP, and they showed that they were able to run molecular dynamics on like a 62 million atom explicitly solvated HIV capsid. And this was for a variety of things. So one, it's architectural improvements to make the models faster. Um, Two, it's like optimizations to like the MD engine, and then three, also hardware optimizations slash engineering ones, being like, okay, like how can we run MD across many different GPUs? So this is being run on across a ton of nodes here. Um, yeah, that's one way it's relevant. Another one is like faster NNPs allow for more accurate protein molecular dynamics. So now, like for really large systems, you can only really do molecular mechanics. And as we've shown, like if they doesn't take any quantum effects into account, it's not super physical. Um, Meaning, like, let's say like you could just do DFT at that speed. You're going to be able to see things that like you just never saw with force fields. And the idea is like with NNPs, if they truly are like as accurate as DFT, but you can get them closer to this force field speed, then you'll be able to see things and discover things that you've never seen before. So a recent paper by Tim Duignan at Orbital Materials, they showed that they found a new reaction mechanism by using OrbV3 to run molecular dynamics on carbonic anhydrase, which is a carbon capture enzyme. Other things we've seen too is NNP embeddings have been used for chemical shift prediction, actually beating state of the art, which is pretty cool. NNP embeddings pretty much meaning, at the end of your model, you have your like energy prediction. If you chop the head off, and you do a transfer learning thing where you really just have like, what are the hidden states of all of your nodes before you do your energy prediction. Uh, you have like a rich representation of like what is going um, on the potential energy surface in that area. So one thing that they've done is they've used NNP embeddings to get snapshots of areas of proteins and then train like a simple like graph convolutional network to predict things like chemical shift. And one thing they show is like, across, changing the ring orientation, you expect like this chemical shift to change in a smooth way. And it does using these neural network potential um, embeddings, but for UCB, which is the current state of the art, it's got this pretty unphysical looking behavior. Um, so yeah, I mean, what's next? There's so much cool stuff to be working on now. Like there's so many cool things that can be done with the OMAL 25 data set that's been released. I think like, what does it look like to train on a really large data set? What does it look like to define a good data distribution? Kind of like, um, what you were saying earlier, um, Christoph, was, like, okay, like one way to define a distribution is, what scale are these forces on? Like you can have diversity on like system size, on like what elements are at play, what reactions are occurring, are you near a transition state? What are the magnitudes of your forces? So if we know that just like more data doesn't necessarily mean better, at least for the current state of things, like, and for this architecture, how do you define a good distribution? Another thing is like, how do you explicitly handle long range forces? Like just increasing the cutoff radius. So long range forces are like within the scope of like the neighborhood of just one specific atom. No, it isn't necessarily a great way to do so. Like if you're just trying to break the energy of that, your long range force uh, component of your energy is going to be so small compared to the the contribution of your covalent bonds that like the signal can be lost there. So AIMNet does a good job at this. We see like latent Ewald summation is a technique people are using. Shui-Ping Ong has like a cool way to create uh, like well-behaved data sets that are larger. I think he was able to train a model on like a really, really tiny subset of OMAT 24 and get almost like really comparable or even better results than a model trained on the entire thing. Obviously, making models more scalable. So like one way that we do equivariance with um, is with we use spherical harmonics, which are just sort of like expensive Wigner D matrix uh, operations, tensor operations. So, we see like acceleration libraries like coequivariance. We also see some people using like Cartesian equivariance so that they don't need to do these expensive matrix multiplications. You see like the Allegro paper. And then another thing too is just using pre-trained neural networks as starting points for small data tests. So, you can use a guidance for generating conformers, as a way to like sort of sample your Boltzmann distribution. Um, I've seen some people do fine tuning for specific reactions. Fine tuning is hard for these. Catastrophic forgetting is like happens almost immediately for these NNPs. But when you start with like a good general model, you can get to something that can model a specific reaction really well. And then things like Admitox prediction or whatever your small data task is, like oftentimes in chemistry, data sets are small because experiments are expensive. And like if you can, generate a conformer and then enrich like the small amount of data you have with a model that's trained on like, much more data that can yield some pretty cool results. So yeah, I mean, I think like uh, one final thing I'll say here is like, why did we do this? Like, why does Rowan care about doing this? Like, we care about just like delivering tools to scientists that like we take this research, we put it in like a way that people who are actually doing experimentation and doing simulation before they do experiments don't need to be experts in computational chemistry or in coding, for example. I can show you a quick example of like you can use Egret on our platform pretty easily. I'll just show an example of, um, we'll optimize ibuprofen here. Um, this is ibuprofen. We're using Egret. We'll run an optimization, and this should take about a minute. But yeah, like what we want to do with Rowan is like, okay, like how can we like trust and show that we're validating, like we know what these models are good for, we know when to recommend them and when not to recommend them. So, people who are organic chemists, people who are designing drugs, like they don't need to be experts in this field. They don't need to know how to program to use these tools. And people who do like to program and, are running like large scale computation, they can use our structured API and, they don't have to worry about not having the compute necessary, the GPUs to run these sorts of models. We and the neural networks, they're energy and force predictors, which are like engines that are used in higher order workflows. So they're engines that are used in our molecular modeling suites. But yeah, we do stuff for like property prediction, macroscopic PK, biology stuff, some docking. We have Boltz 2 on here. Um, but yeah, like the reason we did this was we saw like a gap in this field. We wanted the tools to be good. We wanted them to be open source so people can like make these things better. And we really just care about good tools here. Um,
Yeah, this
So
is an excellent tool. Maybe, while we're waiting for this to finish, if people want to stay up to date with the field, one thing I've been impressed with is your benchmarks. Um, so I believe Rowan also has a benchmarks page that keeps everybody in the NNP field honest, which is always nice to see.
yeah,
Yeah,
yeah, Ari does great work here. We are working on expanding this a lot. I think it's like a good starting point, but we want to make it easy for other people when they design NPs to run them through benchmarks like the ones we did for the Egret paper. Uh, so to validate the usefulness of their NNPs. So yeah, so it just finished. Let's see how long it took. It took like, yeah, a minute, 20 seconds. Um, we can watch the geometry optimization sort of happen, uh, which is fun. As someone who doesn't design molecules, I think like when things move on the screen, it's fun. Um, uh, but yeah, that's like just like a brief demonstration. But yeah, I mean, thanks so much for the time. I'll just open the floor for questions. You can reach out to me at my email here, and then Rowan is free to try.
absolutely. Thanks so much, Eli. Really, really wonderful talk. So, you know, I'm sure we have questions. I'll leave it up to I'll say Christoph and Shaheen if you want to limit yourself to one, if you have one, so we can wrap up. That would be
Yeah,
great.
sorry for going over here, guys.
No, thank you.
My
The
apologies.
demos are great. Yeah, thank you.
I've a very quick question. In your model, you mentioned that there's actually a higher body order sort of expansion going on. Do you control explicitly the order there?
Yeah, at least it depends on the architecture. Using the MACE architecture, that is a hyperparameter that you can explicitly set. So I think for our models, we did a body order of three for our final
Okay.
models. But the hyperparameters are in the paper. But yeah, the body order is something that we're explicitly setting.
Okay. And this is a trade-off between accuracy and sort of like speed, or could you also just put it higher and see what happens?
Yeah, yeah, exactly. It's it's
Okay.
it's, it's that in speed. Yeah, it's just like the number of things that you have, the number of combinations of messages that you're computing just kind of explodes as you increase that.
Hmm.
Mace has a clever way of dealing with this. They sort of they compute the messages across just the two body order, and then they take like the outer product of those two things. Um, and they're taking the outer product of those two things and they're sort of extrapolating the higher body order interactions from like this tensor product, this outer product of those two of the lower body order interaction. So that's pretty interesting. They've shown that it kind of scales linearly if you do it that way. But yeah, that's like a computational complexity versus accuracy trade-off there. But I think they also did in their original paper, they showed that like once you get up to three doing higher body orders, at least at the data set scale that we're working with and the model scale that we're working with, it doesn't really um, provide too many more gains.
Okay. Okay. Thank you.
I have one very quick question again. This was a little bit above the area that I know the details, but on the graph side, I'm curious if people have tried hypergraph modeling instead of just traditional graphs with, pairwise edges, especially for the higher order bodies that you talked about in order to basically model message passing with, not just within edges, but defining hyper edges in that case.
Yeah, yeah, totally. I mean, we see some people doing some like, you know, uh, uh, yeah, some hypergraph modeling. We even see some pretty cool like I think I recently saw a paper. Man, I wish I had like better. I wish I could say the name of the paper so I could tell you. But what they do is they do this like hypergraph construction and then they actually they do so as like a pre-processing step. So they're able to like construct a hypergraph before even running inference. So they don't need to train the model architectures much. And they've shown that they do actually can get better. They can get better performance it's not it's to a limit. It's another thing. It's like okay, you go increasingly higher and higher orders of like of your across like across your graph. But they've shown that it can help. I think one thing is like a thing that I'm skeptical of and people I think are skeptical of is like, okay, like how much more complexity are you adding by doing this like huge like higher dimensional hypergraph? And then how much returns are you actually getting? I find that like theoretically they're super cool and interesting, but empirically we haven't seen like awesome results yet. But there's there's so much work to be done in this field, and like that hasn't been explored thoroughly yet. So like I hope more papers come out where people show those things. Like it'd be really cool and elegant to see if these like really cool theoretic like examples like, oh, this graph can like pass like a two Weisfeiler-Leman test. Oh, like it can really differentiate between these graphs. Actually ends up being super useful for neural network potentials.
Nice. Thank you.
Awesome. And I have one comment and one question. So on the comment side, I am super excited to see how the explorations on data composition unfold because we're not as privileged as natural language processing, where we can look at clusters of data and just say, okay, yes, like we're going to use encyclopedias and not like Reddit to train the model, right? There's a very big difference in quality, but it's not as clear what actually helps the model in these sort of chemical biospaces. And I think it's actually one of the biggest risks in training foundation models. So very excited to see what happens there. And thank you for the very thorough explanation on that side. On the question side, at least two of the levers of like research in this area are like global inputs and long range interactions. And it seems like the explicit choices of the, graph neighborhood are really fighting against, I think, both of these, right? And so architectures have been proposed to kind of loosen this up, but like this is going to sound, so machine learning, but like why not transformers, right? Why not transformers? Why aren't people using these? It seems like these have been the de facto standard in proteins, where we know that long range interactions are incredibly important since AlphaFold 2. So what is it about like this domain that means that graphs are so much better than transformers? Is it really just inductive bias?
I think it's the inductive bias there. I mean, yeah, theoretically, like, what if you just make your graph fully connected and then all of a sudden you have a transformer, right? I think like another thing that's a good example here too is like, uh, the construction of like, GPU hardware is like pretty well suited for a transformer, but not really well suited for a message passing operation. Even though like, let's say you have like a fully connected graph and you're doing like graph attention, like it's maybe fundamentally the same thing. Um, I think an MP-NN is harder to represent as a transformer. But also I think like the the permutation invariance is pretty important for using a graph neural network. But I mean, no, one question that always comes up in my head is like, okay, like why don't you just like do a graph, do attention, um, except your positional encoding is some sort of like molecular graph positional encoding. So you're giving the model that information, and then like just boom, like one you can take advantage of these hardware optimizations, and maybe you can functionally model the same thing. Like I'd love to see some people. I've seen some work in this. We've seen some early work where people actually do just strict attention on these things. We found that like the inductive biases you can add, including like equivariance and other things, um, with the graph neural networks, tend to be useful. But then again, like you have like we just recently we see like really cool like equivariant, like super highly scalable equivariant like Mamba blocks or something. So yeah, like why not transformers? It seems like they're too unconstrained. Like it's too uh it's not doesn't have enough inductive bias. Um, but I think like there's still like people should try harder. Like I think one of the ways that like we might be able to see these scale is with a is by incorporating transformers here. Also, like transformers they're great for they're great for text. Like we found like, okay, your GPT style architecture like is an architecture such that if you scale the number of parameters that you have and you scale the amount of data you have, you can just like pretty reliably trust that you're going to get better results. I think like when you look at like a convolutional neural network versus like a vision transformer, only once you get to like a certain level of amount of like data size does the VIT actually perform better than the convolutional neural network. The convolutional neural network has like translational invariance. It's an inductive bias sort of built in, which helps it at a lower data scale. But once the data get bigger, this more unconstrained architecture works. I think like we see vision models getting better. I don't know if we have like the GPT of vision models, meaning like, look, just throw more parameters, throw more data, like it's just going to get better. And I think like the task just gets harder. Like you have your language, it's a 1D sequence. You move to your images, you have like your 2D representation, and then you move to graphs. You've got like then you move to molecules. You've got like your 3D. You're working with 3D. You're working with like physics that behave certain ways at certain distances and very differently at other distances. Which like just like in the data set size we have now, I think just like requires a lot of inductive bias to like make it still useful. But maybe, on a data set as big as OMAL, a transformer can be useful. I mean, it's big, it's 100 million structures, but like, in like vision, that's tiny, compared to like the data sets we have for language too. So I don't know, like maybe it's not enough inductive bias. Maybe it is. I'd love to see more work doing that.
Yeah, I'm interested. It feels like almost a stupid question. Why don't we use transformers? Like almost certainly somebody's tried it, right? But it's
Right.
like, there's a dog that doesn't bark here, and it's sort of interesting to figure out why. Um, but no, thank you, Eli, so much. This has been a wonderful talk, bridging, I think, both sides of the domain of foundation models for biology and biochemistry. And I really, really enjoyed it. So everybody who's still online, please go check out Bro and Sci. There's, I believe, free compute credits.
Yep.
Go check it out. They make nice tools if you want to play around with anything that Eli presented in the talk today. Okay. Well, thanks so much, and see you next time.
Cheers. Thanks so much.
Thank you. Bye.
Bye.